Oftentimes, scientists need to calculate the amount of energy needed for a combination of enthalpy changes. They might take 57 grams of ice at negative 25 degrees Celsius, heat it to its melting point, melt it, and heat the liquid to 20 degrees Celsius. You might be thinking, this is easy. I know the formula I need to use. I need to find heat. I have a mass, I can look up a specific heat, and I have two temperatures. But you can't apply this formula once you're going through a phase change. You don't have ice throughout that temperature range. You're dealing with the heat capacity of ice in one area and the heat capacity of liquid water in a different area, and those are two different numbers. Specific problem, we have to deal with enthalpy of fusion as well. The first thing we're going to do is draw a little diagram to help illustrate the example. So we're starting with ice. We heat that ice until its melting point. Then you go from 0 degrees Celsius ice to 0 degrees Celsius water. Then you heat water to 20 degrees Celsius. Here's what that process could look like. So for our first step of heating, going from ice below 0 to ice at 0, that we can use the heat capacity of ice and that temperature change for that segment of this process. That means we can use this formula. The change in enthalpy with our mass of ice, the heat capacity of ice, and the change in temperature just for this segment here, these 25 degrees going from below 0 to 0. That step right here. Once you have ice at 0 degrees Celsius, we can't use this formula anymore. You're going through a phase change. That means that we're no longer dealing with the mass of ice, we need the moles of ice, and we'll use this formula. Once we're through this segment and we have totally converted the ice to liquid water, we are done separating the water molecules enough to be considered water. Then the rest of that heat energy can go into heating liquid water to 20 degrees Celsius. So we're back to using this equation, back to using our mass. Our mass hasn't changed. 57 grams of ice is now 57 grams of water. We'll use the heat capacity of water and this 20 degree temperature change right here. So the enthalpy formula is going to look like this. Dealing with ice for this segment, dealing with our phase change for this segment, and dealing with water, liquid water, and that temperature change here with this formula. Notice your heat capacities are changing, and here we don't have the heat capacity, we have heat of fusion that we're dealing with. Before I start rewriting this formula and trying to solve, there are a few things to note. It's probably going to be easier to take our mass of ice and convert it to moles first and have that number ready to go. Also, there will be a mix of units of heat, kilojoules and joules, so we have to be careful to keep our units the way they show up in these formulas and keep note of them. So step one, we're going to solve for the amount of moles. That's our mass divided by our molar mass. So we have 3.16 moles of water. Ice in this case. Instead of writing all of these numbers, m, Cp ice, delta T, and on and on and on in one long equation, I find it easier to break this up into different delta H's that we'll find, 1, 2, and 3, and then we can just add that at the end. So for step one of our heat, You can look at the formula here. That's going to equal the mass of this ice, the heat capacity of our ice, and the change in temperature. Remember, change in temperature is final temperature minus the initial temperature. Heat capacity of water is in joules per gram degree C. Delta T means temperature final, so where we end up at this segment, 0 degrees C. So that's final minus initial. And this right here is how you're going to get a positive delta H. You need to add heat in order to get ice from below 0 to 0. So for this segment, we have 3,004 joules that we have to add to get to ice at 0 degrees Celsius. Now we're ready to look at a phase change. The formula we're going to need to use for this, number of moles times heat of fusion. And we already looked at the calculation for moles, so we have that ready to go. Heat of fusion this is in kilojoules per mole. And finally, our last heat, taking liquid water at 0 degrees Celsius and heating it to liquid water at 20 degrees Celsius. Final temperature 20 degrees Celsius. Initial temperature is 0. That's final minus initial temperature. We're using mass again, so back to 57 grams, 4.184 joules per gram degree Celsius, times our temperature change of 20 degrees Celsius. And this is in joules. You can't just add these numbers together. That's like adding pounds and ounces. You need to convert either your two measurements in joules to kilojoules or convert your kilojoules to joules and add them all up. And that's what we're going to do. We'll take this one measurement in kilojoules and convert it to joules. In 1 kilojoule, there are 1,000 joules. You can see that. So you have to multiply this by 1,000, and that is equal to nearly 19,000 joules. Now we can add these numbers together. $26,754 joules. You could see where this problem could continue on. You might have to get your water through another phase change, reach 100 degrees Celsius, convert to steam, and then keep adding heat. So you might have to continue with a fourth step. You just have a longer delta T and this, and then move on to heat of vaporization, deal with that enthalpy change, and then go back to this formula with a heat capacity of steam. Essentially, the steps to solving these types of problems: draw out what you're trying to do, then put the formulas for each step that you would need, convert to moles, don't forget that, watch your units, do it in steps so you can check your work.